Uh, Good morning, everyone. How are you today? Good. Right. Not so good. Not so bad. Again, before we get started to our lecture today, let's recall what we have learned last week. Last week, we learned semiconductor. I hope you still remember, and we know that there's a band gap between um, valence band and conduction band. So this is place we call band gap. In comparison to metal, there's no band gap because the band overlapped. So the band gap means that uh, in order to have, in order to let electron go to the conduction band from valence band, you need energy. That's why we call it semiconductor. Okay, for the semiconductor application, for the semiconductor are the photovoltaic, and then for LED. That means that if we give the energy, photon energy to this semiconductor, the this semiconductor will produce electricity. This is called photovoltaic. You know, we use solar panel, and this is the application for the semiconductor. On the other hand, if we use the electrical power to give the energy to this semiconductor, and electron will jump from the valence band to the conduction band. And then when you cascade from the conduction band to the valence band, energy will come out, and this in the form of the photon. So that's why we call LED light emitting diode. So these are the applications for the semiconductor. And also we introduce you the band gap engineering. You know, we can tune the gap, the band gap, by using different type of semiconductor, and we put it together. This is what we call compound semiconductors. And finally, we introduce you the excitation of semiconductor. That we introduce you three methods. The first method is the one we start is called photon excitation. Photon excitation is using the photon energy to realize the band gap of the semiconductor. And second one is called thermal energy, thermal excitation. We use thermal energy to to excite the semiconductor. Finally, is called chemical excitation. The chemical excitation is that we introduce different type of the elements into the silicon. For example, if we introduce uh, elements in the 3A group, that means boron, for example, into the semiconductor, into the silicon semiconductor, and this is what we call P-type semiconductor, right? Positive semiconductor. And we have more electron holes in the semiconductor. And then if we introduce the type 3A or 5A group, if we introduce elements in the type 5A group in the periodical table, for example, like phosphorus or sulfur, phosphorus or arsenic, then we produce N-type semiconductor. N stands for negative. So we have more electrons in the semiconductor. Okay, so this is what we use uh, nowadays in the semiconductor industry. We call chemical excitation. We introduce different type of elements which has different valence electrons. Okay, so uh, this is the summary of a semiconductor. And after that, we introduced what's the meaning of gas, liquid, and solid. The meaning of the gas, liquid, and solid is that what we know is that uh, here is cohesive forces versus destructive forces, right? So that means we have bonding energy against thermal energy. So if your bonding energy is high, the thermal energy is low. That means it's easy to form solid. If the thermal energy is higher than the bonding energy, much higher, that means this state, the element, the material in the state in the material will be in the gas state, right? So we are always talking about bonding energy against versus the thermal energy. This is what we call the secondary bond. The secondary bond is that we can call it secondary bond or van der Waals bond. And then before we introduce secondary bond, and we need to know that the dipole interactions. So last week we already introduced you in dipole interaction, right? And we also give you an example of the polar molecules. This is secondary bond force. So last week we introduced you the dipole interaction. I hope you still remember. We use a case of the hydrochloride, and we know that the bonding energy is related to the distance between molecules and the distance between atoms. These are important for you to know. If the distance between the two molecules is high, that means what? That means it's easy to form. The energy is high, right? The distance here the distance here is short, then the energy is high, will be high. If the distance between this is short, that means this will be low, and it's also related to the what? To the temperature. Okay. Right. So and I also give an example of sodium chloride in gas phase, sodium chloride in liquid phase, sodium chloride in solid phase, and aqueous, what we call the sodium chloride solution, or we call hydrochloric acid. Right. So today, we are going to talk about the second interaction called dipole-induced dipole interaction. So for the dipole-dipole interaction, we use an example of polar molecular and polar molecular interaction. And now, the second interaction, we use an example of the polar molecular and the induced dipole bonds interaction. What does this mean? Let me show you here. So you know the dipole-induced dipole interaction, for example, the present in the solution of a one polar and a non-polar species. So you have two species. One is polar molecular, one or polar species. It can be molecular or it can be atom. So one polar and one non-polar species. So for example, again, we use the example of hydrochloride. So this is hydrochloride, and this is a polar molecular. So when we introduce, so of course we have dipole here, which is positively charged and negative charged. So this is called polar molecular, right? Okay. So if we have an atom or molecular, which is non-polar molecular or non-polar species, and this atom is close to this polar molecular, then what happened? Let's use the argon as an example, because I have negative charge in this region. So the argon, if the argon is close enough to this molecular, and this part will be the electron will be more close to will dislike this region. Why? Because it is negative charge. So this place will have more positive charge, and this place will have more negative charge. Again, if the argon atom is close to this hydrochloride molecular. So this is called induced dipole. Okay, this is called induced dipole. So This is delta plus, means that electron deflection or electron diffraction. Okay, you don't have most of the electron in the outermost shell will close to this part because this part is negative charge. So this region will be electron-rich region. And then if you have positive and negative charge, then you will have Coulombic attraction to each other. And this is a van der Waals force. Again, you have the third molecular or another molecular come. We can assume this is hydrochloride again. So, and this is because, this negative charge won't come to this part because, this will have positive and positive repulsion. So you want to attract, the molecule want to attract to each other. So the positive charge will be in this part, negative charge will be in this part. And again, there's a bonding energy, there's attraction between each other. And this is, again, this is how we form the bond. So another argon come here, and then you have positive charge region and negative charge region. And again, you have bonding energy between both species. How about energy? Again, the energy is the proportion of the reciprocal of the R. R is this distance, power 2, right? If this is closer, then the energy will be high. If this is far, that means R is large, then the energy will be what? The energy will be low. So let's have some more explanation about this dipole-induced dipole interaction. So this is called electrical polarization. Is that what if we have, again, the previous page I just showed you that if we have argon species here, and of course you have positive charge and negative charge here, and we have energy bonding energy between both species, right? So now I give you an example of helium. So, and then I ask you a question. The energy between hydrochloride and argon and the energy between the hydrochloride and helium, which bonding energy is high? This one or this one? This is called polarization. Polarization. Can you tell me which bonding will, you have a bond between hydrochloride and argon, you have a bond between hydrochloride and helium. Which bond will be higher? Energy. Bonding energy will be higher. Have a guess. When we're talking about bonding energy, we're talking about Coulombic attraction. If the Coulombic attraction is high, the bonding energy will be high. So compared to argon or helium, which bonding will be, energy will be high? Oh, attraction will be high. Anybody want to tell me? Okay, the answer is argon. This is called polarization. Why? Polarization is that electrical charge displacement. How huge is the electrical charge displacement? If the displacement is high, then polarization will be high, then the energy will be high. So this is what we call electrical polarizability. It's what is the measure of the ease of the electrical displacement. So displacement, this one higher than this one or lower than this one. Of course, argon will be higher. Why? Because the size of atom is big. So the electron in the outermost shell cannot be controlled by the nucleus easy compared to the helium. Because the electron in the outermost shell is closer to the nucleus compared to the argon. So what's that? So the alpha electrical polarizability is the proportion of the electrons. How many electrons you have, and what's the size of your species the species? Okay, so if we have more electrons, that means the polarization will be high. If you have a large size of the species, the polarization will be high, or the polarizability will be high. We call alpha. And alpha is very important because alpha dominates the form of the gas, liquid, or solid. We are going to talk about this very soon. Okay, so for the polarizability, argon will be higher than helium. Why? Because the number of electrons are more, right? You have more numbers of electrons, and most importantly, in this case, is the size of argon is higher than the size of the helium. So the measure of the electrical polarity of the system of the charge we call P. P is that, this related to the force. Okay, so P is the alpha times E. E is the electrical field, and alpha is the polarizability. So you can measure the electrical polarity of the system using this equation. But important things in this page, the things I want you to know is what's the polarizability. Okay. So let me give you some description more about the polar molecular and induced polar dipole bonds. Again, you have hydrochloride and you have atoms, which is neutral. There's no induced dipole or dipole here. And then when this species close to this hydrochloride, and then polar molecular can also be induced dipoles in adjacent nonpolar molecular atoms. This is called adjacent nonpolar moleculars. And a bond will form as a result of attraction forces between two molecules or between two species. So when this one close to this one enough, you change to the dipole you will find a dipole in this species, and this dipole is called induced dipole. Again, non-dipole, right? And close enough become dipole. This is what we call induced dipole. And there's force between each other. We call van der Waals force. The energy we call van der Waals bonding force, energy. So the magneticity of this bond will be greater than for the fluctuation-induced dipole. What is fluctuation? What is fluctuating induced dipoles? We are going to talk about this in next page, in the following page. It's called induced dipole interaction. So the third interaction is called induced dipole interaction, or we can call it fluctuating induced dipole bonds or fluctuating induced dipole interaction. Let me give you an example of argon ice. Argon is a form of gas at room temperature, right? So can you realize what's argon ice? I hope you still remember we talk about solid hydrochloride. If the temperature drops lower enough, the bonding energy is higher than the thermal energy because temperature is low. So you will form the solid hydrochloride, right? And that means that the molecules of the hydrochloride will be very, very close and become a solid form. And how about argon ice? What kind of force or what kind of energy form this argon ice? Because you have dipole, right? You have dipole between the hydrochloride molecules. But what's the force between argon species or argon atoms? So argon, let's think of this step by step. Argon gas, right? If you drop the temperature down to the 87 Kelvin, then argon gas will become liquid argon. And if you drop the temperature down to 84 Kelvin, it will become argon ice. So in the reality, you can make argon ice. So if you take the argon ice out from the temperature of 84 Kelvin and to the room temperature, the argon ice will melt immediately. And this is melting argon ice. You can see the vapor and the water and liquid argon dropped. And soon or later, very soon, you will become gas, argon gas. So when we think of this, that means what? The argon atom close to each other, very close to each other. And this is called solid argon, right? So according to what we learn, what bonds argon and to argon together? Because you need to have an interaction between both argon's atoms, so you can have a bonding energy. In order to have bonding, you have bonding energy, and you need to measure the thermal energy, right? If the bonding energy is higher than the thermal energy, you can make a solid. Okay, so is this bonding argon and argon, the bonding is ionic bonding, primary bond? No, certainly not, right? How about primary covalent bond? This is not covalent bond at all. And I'm sure you understand that between these molecules is called intermolecular bonding, which is belong to the secondary bond. It's not primary bond. The secondary bonding is this dipole-dipole bonding? No, there's no dipole. Argon is not a polar molecule, so there's no dipole, right? And this argon is not a dipole. So this is not a dipole-dipole bonding. How about dipole-induced dipole bonding? This is not dipole, this is non-dipole. There is no induced dipole. So when in the previous century, the scientists think of this over and over. What kind of energy between the argons? So this is called London dispersion force. This is a German-born American. He proposed this theory, say that, wow, this is London dispersion force. It's induced dipole interaction. So this is called induced dipole interaction. Is dominate in the nonpolar species. So when you have nonpolar species, you also the dipole can be also created. Why? This is what we try to explain to you. It's called London dispersion force. We use LDF for short. Why? You know, electrons are in motion. So electrons move in the atoms with the time, right? It can be time 1 here, time 2 here. And as I just told you that when we learn the quantum mechanics, they tell us, the quantum mechanics tell us that electron, we cannot find where is the electron, and which also is difficult to find the speed of the electron and the location of electron in the same place at the same time. Okay, so we understand, for example, for time 1, for example, this might they might have more electron accumulate in this place, and this is what we call the delta minus, and this delta plus. This time 1. Okay, time 1. And at the time 1, that because the electrons from the different molecules atoms start feeling and avoiding each other. So this adjacent argon start to fill this dipole and then avoid each other. Electron density in a molecular and atom become redistributed in a proximity to another electron molecules or electrons. Another molecules or atoms. But in this case, argon is a atom, right? So at time 1, if this is electron deflection, and this one will be electron-rich region. And if this is electron-rich region, you'll find out that the opposite side, this will be electron-rich region. And again, if this electron deflection region, and you will find out this is electron-rich region, because at time 1 this is induced and induced. So this is called induced dipole interaction. Okay, this is frequently described as a formation of instantaneously dipoles that attract each other. So at the time 1, the electron distribution might be like this, but at the time 2, this electron distribution might like this, and then this, right, and this. So it depends on different timing. You have different electron distribution, and this is called London dispersion force. And we also call this time fluctuating dipole. This dipole change with the time. So LDF London dispersion force is present in all the systems. In the primary bond, the energy is high. Secondary bond, the energy is low. And LDF London dispersion force, the energy is the lowest. It is present in all the systems, but you cannot tell. You cannot realize because the energy is too low. So here I give you 2 examples. London dispersion force. For the atom to atom, it's like helium. In the beginning, there is no polarization if they are very far to each other. Once they close to each other, because of the distribution of the electrons, you have electron depression region, and you have electron-rich region. And then this is called instantaneously dipole on atom A. And once you have instantaneous dipole on atom A, and if the atom B close enough to the atom A, this atom induced dipole will be on the atom B too. Okay, this is called atom to atom London dispersion force. How about molecular to molecular? For example, if you have hydrogen gas, and this is not polarization, hydrogen gas, and then in one case, this is if they are close enough, the instantaneous dipole on molecular A at time 1, and this is time 1, and here you produce the electron-rich region, and this is electron deflection region. And then sooner or later, at the same time, I should say, the induced dipole on atom B will show up if they are close to each other enough. Okay, so London dispersion force is the intermolecular forces inhibited by nonpolar molecules or atoms. Okay? And a part of the van der Waals forces. These are all called van der Waals forces, which is secondary bond. So the energy is the proportion of alpha. Alpha is what? Polarizability, right? Polarizability. R is what? Interspecies separation. So atom molecules, if the atom and molecules, the size is high, and the London dispersion force will be high. So the increased permeability of the molecules with large and more dispersed electron clouds. So again, once your molecule is high and your molecule is large, or atom is large, the electron in the valence shell is far away from the center of the nucleus. So electron cannot be controlled very easily. So you have more easy to make dipoles. So the force or the energy between atoms will be strong, will be high too. So here I give you an example of this, the size. At room temperature, fluoride is in a gas phase, is in a gas form. Chloride is in a gas form. But if the size is higher, its size is bigger. Boron is in a liquid form. Molecule is in liquid form. Iodine is in a solid form. That means what? That means that the energy, because the size is higher, the atoms or the molecular between the intermolecular force will be high. Okay? So larger amount of surface contact also, if you have a large amount contact, and you will see London dispersion force will be higher. I'm sure you understand this, right? Are you with me so far? Okay, good. So greater surface area means a closer interaction between the different molecules. So here is the iodine crystal. Have you seen iodine crystal? Yes, it's in a solid form. You have other iodine molecules. This is molecular. And then if molecular and molecular close enough, it becomes a solid, right? So you have LDF, London dispersion force. And because this iodine size is very high, so you have, for example, you have negative charge here, positive charge here, and you also, this will be induced, right? So this is positive, negative charge, positive charge. This is an example of two molecules. If we have one more of the iodine molecules, you will become a solid. You will become a bulk material. So this is intramolecular. This between iodine and iodine. This is what? This is covalent bond. And between iodine and iodine molecular, this is what we call fluctuating induced dipole bonds, and caused by LDF. Okay, this is fluctuating induced dipole bonds. This is covalent bond. So if you have one more of the iodine molecule, you put it together. This is what we look in your naked eyes. Okay, you can have iodine solid at room temperature. Of course, what you can see is if the temperature is higher, on the surface of the iodine molecule will be vaporized. So you will see that because the bonding in the surface is weak. So if the temperature is a little bit higher, the iodine molecule will be vaporized. And you can see something like this. Because it vaporized and dropped. So now, can you realize how we can find a solid meson in a Jupiter, in another planet? Meson is a non-polar molecule, right? If a non-polar molecule, how can you make a solid? By what? By London dispersion force. Right. So London dispersion force, we also introduce a polariability, right? We call alpha. So this is another example to tell you that this is hydrocarbon. And the difference between these three hydrocarbons are only the size. This is smaller size. This has a 6 CH2. This has a 18 CH2. So this, as you can see, the size is larger than this. It's a chain, a long chain. So the size is more, and this is propane. This is octane. This is icosane. And as you can see, of course the molecular weight is increased once the size of the chain, the number of the chain increased. And as you can see, the boiling temperature and melting temperature increased. Why? Because this chain is longer. And this bonding between each other is stronger. I mean, it doesn't mean covalent bond. It means the between the chains. That means what? Secondary bond is higher because the size of the molecule is high. So as you can see, this propane is in gas at room temperature. This neutral gas, right? And then this is liquid at room temperature. This is what? Icosane. Where do you use? When you use a cooker, you use propane, right? It's in the gas form. So why is this? It's gasoline. Gasoline. When you need your engine on, or your jet engine, this is gasoline. And it's okay. So its polarizability is also related to the size of the molecule, and also related to the number of electrons. So this is another example to show you that these are the hydrocarbon. This C1, C2, C3, C4, C5 until C12 hydrocarbon. And this is molecular weight. Of course, you have more carbon, your molecular weight will be increased. This is the boiling point. And of course, you understand the room temperature is about 25 Celsius. So as you can see, the C1 to C4 is in the form of a gas, okay, at room temperature. And above C5 to C12, this hydrocarbon is in the form of liquid. Why? Because of the size. So once you want to talk about the size, we say that, well, if you have an exam, or if you have an interview, I give you this picture and I say, please tell me why C1 and C4 are in the form of gas. Why C5 to C12 is in the form of liquid. If the explanation is that, well, Professor, because of the higher molecular weight, if we have higher molecular weight, we have a higher boiling point. This is right, but not 100% right. Because when we talk about the gas, liquid, and solid, we always think of what? Alpha. Alpha is the polarizability. So if your explanation is, well, because the different polarizability, then that means that you have better sense of the solid, liquid, and the gas. So for the alpha is number of the electron and size, because the electron the size is higher, large, right? So if the molecular size is large, you have better polarizability. If you have a better polarizability, then the boiling point will be high. This is a correct explanation for this graph. So the gas, liquid, and solid is about polarizability. And the polarizability is a proportion of the number of the electrons and the size of the molecule. Okay? So fluctuation-induced dipole, there are some explanation. I just want to do this quickly. The overall spatial distribution of the electrons is symmetric and with respect to the positively charged nucleus. So you have this positive charge, you have negative outside. And all atoms are experiencing constant vibrational motion that can cause instantaneously short life distribution. Remember, short life distribution. the distribution of the electrons change with the time. Okay, so the short-lived distribution of this electrical symmetry for some of the atoms or molecules and creation of the small electric dipoles. Okay, so van der Waals bonding, the one of these dipoles can be turned, produce a displacement of the electrons distribution of adjacent molecules or atoms, which induce the second one. This is the second one, right? Also, to become a dipole that is weakly attracted or bonded to the first. This is one type of van der Waals bonding. So if we have a one adjunction to this fluctuation dipole, this will also be induced to become a fluctuation dipole. And then between each other, there's a van der Waals force. So these attraction forces are temporary and the fluctuation with time. Right, just give you an example here. So now we talk about three types of interaction: dipole-dipole interaction, dipole-induced dipole interaction, and induced dipole interactions. How are you going to compare these energies between these three? Which one is the largest? Largest is this one, the permanent dipole bonds. Of course, you understand, because dipole-dipole interaction, the dipole is permanent dipole. So when you have interaction between permanent dipoles, the bonding will be strong, right? So the dipole-dipole interaction, the energy of the dipole-dipole interaction will be stronger than what? The dipole-induced dipole interaction. And I need you to remember is that there are three factors. There are three important factors between this one. Is that R is the distance between molecules. D is the distance between atoms, and the temperature. These are the energy which will proportion to these three important factors. And of course, the polar molecular induced dipole bonds, the energy will greater than fluctuation-induced dipole, because this is the weakest. Fluctuation-induced dipole, the energy of the fluctuating-induced dipole will be the weakest among these three. Okay? Right. So there's a special case in the van der Waals force or in the van der Waals bond. It's called hydrogen bonds. Why hydrogen bond is a special case? Because a hydrogen bond has only one electron. And if you move this electron from one side to another, the side where has no electron will be only bare. There's no protection of electrons for the nucleus. So the bonding will be very, very strong, because you have very strong negative charge region and you have very strong positive charge region, because you have only one electrons. Okay, if the electron move, and you will have very strong bonding. This is what we call hydrogen bond. But before we talk about this hydrogen bond, next topic is hydrogen bond. What does that mean, hydrogen bond? Hydrogen bonding occurs between hydrogen and only the most electron-negative elements. What does this mean? Most electronegative elements. We have electronegativity. We have a number of electronegativity for all the elements. For example, fluorine is 4.0, oxygen is 3.5, chlorine is 3.0, boron is 2.8. This is called electronegativity. I hope you still remember. So we want to pick up the best three numbers. They are fluorine, oxygen, and nitrogen. Well, chlorine is about 2 point something, 2.8, but here is 2.9 or something like this. Okay, so these three are the highest electronegativity, the number of electronegativity. And hydrogen is the lightest element, which has only one electron. So when you have hydrofluoride molecular, and of course you understand this is negative charge region, this is positive charge region. Why? Because fluorine likes electron very, very much. So if you have one electron here, and then this one will be, electron will be pulled very close to fluorine. So you have very good electronegativity, very good negative charge region. You have very good positive charge region. And this is called bare proton, because there's no electron to protect this hydrogen anymore. As this electron will be very, very close to fluorine atom. Okay, and we understand this is what we call polar molecular. And the bonding of this hydrogen and fluorine is what? Covalent bond, right? Covalent bond. However, if you have another molecular, and this molecular is, again, is a fluorine hydrofluoride, and if these two close enough, and you understand this like electron very much, this electron will be pulled to here. So the bonding is very strong, and also you have very good electronegativity in this region. And again, if you see negative charge and positive charge, this is covalent bond, and this is what? Van der Waals bonding. This is between negative and positive. This is secondary bond. We call Van der Waals bonding. And we all understand, because this is dipole molecular. So this is called dipole interaction. And the energy we call the energy of the dipole bonding. Right? And because this is a bare electron, so the bonding is much strong, is the strongest in the dipole interaction molecules. Why? Lone pair electrons interact with the bare proton. This is bare proton, and this is lone pair electrons. So this is what we call hydrogen bond. Secondary bond, but hydrogen bond. So once you have hydrogen, and this atom is fluorine, oxygen, or nitrogen, and the bonding between these two molecules is called hydrogen bond. Is that clear? It's clear, right? So don't mix up the bonding between atoms and between molecules. And also, hydrogen bond is also related to AVEE. I hope you still remember the full name of the AVEE. It's called average valence electron energy, right? So this 24, 20, 90, these three are the highest. Then chi is electron negativity, which are the highest. So hydrogen bond is a special case of the polar molecular bonding and the dipole-dipole interaction, right? So it occurs between molecules in which hydrogen is covalently bonded to fluorine, oxygen, and nitrogen. I just told you this, right? Hydrogen end of the bond is essentially a positively charged bare proton that is unscreened by any electrons. This is unscreened. There's no protections for this hydrogen by the electrons, because there's no electron here. Okay, so hydrogen bonds, this highly positively charged end of the molecules is capable of a strong attraction force with the negative end of the adjacent molecule as shown here. So this single proton forms a bridge between two negative charge atoms. This behavior forms behavior like a bridge. Okay, so the magnitude of this hydrogen bond is generally greater than that of the other type of the secondary bonds. So hydrogen bond, as I just told you, that is about 21 kilojoule per mole, and which is about 0.25 electron volt per molecule. So the energy is high. The bonding energy is high. I hope you still remember when I told you, I want to let you know that the sense of the energy using the unit of the electron volt. For example, what's the energy at room temperature? Remember? What's the energy of the room temperature? 1 out of 40 electron volts, right? So once you have hydrogen bond, and we also told you that this is secondary bond is related to the gas, liquid, and solid. So if the hydrogen bond is 0.25 electron volt, this is called bonding energy. And once we want against the thermal energy is what? It's 1 out of 40 electron volt. Which one is higher? Hydrogen bond is higher, right? So once you have a hydrogen bond, it's easy to form liquid or solid compared to the gas. So once you have hydrogen bond, you will see that if you have hydrogen bond, it's easy to make as it's in the form of the liquid at room temperature. So the melting point and the boiling point temperature of the hydrofluoride and the water H2O are abnormally high in the light of their low molecular weights because of hydrogen bondings. You know, when we talk about gas, liquid, or solid, is related to the permeability. Permeability is related to the number of the electron and the size of the molecule. But this is different case. If we have hydrogen bond, this is different case because, you know, hydrofluoride and the H2O are in the liquid form at room temperature. Why this kind of small molecule can be a form of liquid because of hydrogen bond. So H2O example here. So as we know, H2O is here. This is bonding. O and H is a covalent bond, right? And then you have positively charged bare proton here, and you have a lot of electrons in this place. So you will have what? You have the outermost shell. There's no bonding electrons, oxygen, right? So you have hydrogen bonds between water. This is a polar molecule, right? Very strong bondings. This is the length of the bond. This is the length of the bond intramolecular. Okay. Right. So this is another example show you the hydrogen bond compared the boiling points of the molecules with hydrogen bond. So let's take a look at our first example. This is a period, right? And this is boiling point. And if this boiling point is increased for the group 14, this methane, silane, germanium H, I don't know how to read this, GeH4, and TIM, right? So once we think of this, the permeability is the proportion of number of electron and the size of the molecule. So as you can see that carbon, silicon, germanium, tin, the size increase. If the size increase, what does that mean? Permeability increase. If the permeability increase, the boiling point increase. It makes sense. It makes sense, right? Okay, so So for group 14, it's tetrahydride, methane, silane, GF4, SNH4. So the temperature increase. The boiling point increase. So you can replace this to become carbon, silicon, germanium, tin, and this size become bigger, right? Because size of carbon small, size of the silicon increase, germanium increase, and tin increase. So molecular size increase, and what? Electron number increase, right? Number increase, valence electron, and then probability increase. If the probability increase, what does that mean? Induced dipole increase. This is nonpolar molecular, ladies and gentlemen, nonpolar molecular. Induced dipole increase, and boiling point increase. If this picture show up in your final exam, I want you to compare the boiling point of these molecules. Can you tell me? Can you explain this to me? Okay, so let's take a look of another group, which is nitrogen, phosphorus, boron, and iodine. And as you can see, well, for your common sense, ammonium should be somewhere around in this place, right? Because the size increase, the number of the electron increase, the probability increase, right? And here, of course, this is induced dipole increase, and boiling point increase. But why this ammonium, the boiling point is high? Why? And also fluoride, the temperature is high, the boiling point is high. Also water, the boiling point is high. This is abnormal, right? Why? Because of hydrogen bond. Okay, so group 5, again, group 15, this is group 15. You can follow the same idea and just change from the polar molecular. This is polar molecular, this is non-polar molecular. This is polar molecular, and also if you think of the size decrease, the probability decrease, and the dipole interaction decrease, and the van der Waals form decrease. That's why boiling point decreased. And 3 special case is hydrogen bond. Okay. So here are some explanations. Right. So now let's discuss the properties and the relationship of the physical properties and the secondary bond. Let's use the melting point first. For example, this is bond length. You have 2 molecules, and this is bond length we call R. And again, you want to think is cohesive forces versus destructive forces. Destructive force means what? Thermal energy. This is bonding energy, right? So you also can use these figures to explain this. The bonding energy, the lowest you will get a very stable state in this place, right? The bonding energy is the lowest, so you got the most stable states in this place. And this is called what? R0 is what? Equilibrium spacing, right? This is bonding energy. This is bonding energy. The distance between 2 molecules or 2 atoms or 2 species is called equilibrium spacing. However, if you take a look of these 2 curves and the melting point Tm, you have if you have two cases, the case 1, this one, case 2, this one, which one has a higher melting temperature? Which one? If the bonding energy is high, that means what? Melting point will be high, right? Because we are talking about cohesive forces versus the destructive forces. So the bonding energy high, that means what? If you want to melt this object, if you want to melt this substance, you need to have a higher temperature, melting temperature. You need to increase the temperature in order to let it melt. So large Tm, and of course this small Tm, right? Smaller Tm. This melting temperature. So bonding energy is related to the melting point. This is the property, right, of the material. So Tm is larger if the E0 is larger. And how about this one? Coefficient of the sum. This is the expansion of the objects related to what? I'm sure you all learn this is coefficient of thermal expansion. This is temperature differences, and this some coefficient of thermal expansion, right? If the coefficient of thermal expansion is high, that means what? This one will get longer at the same temperature, right? If you increase the delta T, and the coefficient of thermal expansion is high, and of course you got a longer in one direction. Okay, this one increase and delta L increase. So again, let's take a look of this. This is bonding energy E0, two objects 1 and 2, for example. So alpha is symmetric at R0. So you stay here, and you have, this is what? Large R, large coefficient, thermal coefficient Y, because the bonding energy is low. So thermal coefficient will be large, right? Because the bonding energy is weak. If the bonding energy is high, that means what? It's difficult to pull it apart. So thermal coefficient will be what? Will be small, right? So alpha is large if E0 is small. So this is another property, thermal coefficient property, or thermal properties related to the bonding energy. Especially here, we are talking about secondary bonding energy. Right, these are the example for you to see just for your information. So for covalent bond, you have higher melting point. You have bonding energy high. You have very, very high bonding energy. You have very small bonding energy. Right, this is the table I summarize all the properties, all the information, some of the important information for you. So this part is primary bonding, this secondary bonding. Primary bonding has 3: ionic bond, covalent bond, and metallic bond. And we already played Kahoot last week. Ionic bond is non-directional bonding. Covalent bond is directional bonding, and the metallic bond is non-directional bonding. A secondary bond is always is equal to van der Waals bonds. Van der Waals bond is directional bond. Why? Because of dipole. Dipole is direction, right? And the special case for the secondary bond is called van der Waals hydrogen bond. Okay, and these are the cases. And for you to see. And here is the bonding energy. You know, bonding energy for the ionic bond, the energy will be between 3 to 8 electron volt. And for covalent bond, it can be very weak and very small. So the range is high. Also, as well as for the metallic bond, the energy level will be very small and to the very large. However, the only one concept you need to know is the primary bond, the energy of primary bonding is larger than the secondary bonding. Because as you can see that is the van der Waals bond is about 0.1 electron volt. Compared to this primary bond, the energy of the secondary bond is always low. However, there's one which is is highest, which is hydrogen bond. Okay. So this is water is very important. You know, without water we cannot survive. And thanks for the hydrogen bond, right? Because water is in the form of liquid, and this is dipole. This is a dipole molecule. So I have a video for you here to let you see that. Okay, before I show you the, this is you know, nowadays it's called Néron generator. Néron generator is that you have a tribal electrical effect. You know, tribal electrical effect is that if you use this, if you use different materials, and you produce tribal electric. And then if you produce tribal electric, you will have charge, negative charge and positive charge. And if you move these two objects, you can generate a very small power. And this is what we call Néron generator. And this is a great, very important study nowadays because energy is very important. And why we talk about this? Because I'm going to show you a tribal electrical effect